Fluid is a non-solid state of matter. All fluids can flow and exert pressure evenly in all directions. You have something in common with a dog, a seagull, and a dolphin. You and all of these other living things spend a lifetime moving through fluids. A fluid is any material that can flow and that takes the shape of its container. Liquids and gases are fluids. For example, you could fill a fishbowl with water or with air. Each would take the shape of the bowl. Fluids can flow because the particles in fluids move past one another easily. Fluids and pressure. You have probably heard the terms air pressure and water pressure. Air and water are both fluids. All fluids exert pressure. So, what is pressure? When you pump up a bicycle tire, you push air into the tire. And like all matter, air is made of tiny particles that are constantly moving. Look at Figure 1. Inside the tire, the air particles bump against one another and against the walls of the tire. The bumping of particles creates a force on the tire. The amount of force exerted on a given area is pressure. So, any force, such as the weight of an object, acting on an area creates pressure. Calculating pressure. Pressure can be calculated by using the following equation. Pressure equals force divided by area. The SI unit for pressure is the Pascal. 1 Pascal is the force of 1 Newton exerted over an area of 1 square meter. Pressure and bubbles. When you pour a carbonated liquid into a glass, you can see gas bubbles in the liquid. Why are the bubbles round? The shape of the bubbles depends partly on an important property of fluids. Fluids exert pressure evenly in all directions. The gas in the bubble exerts pressure evenly in all directions. So, the bubble expands in all directions to make a round shape. Atmospheric pressure. The atmosphere is the layer of nitrogen, oxygen, and other gases that surrounds Earth. Earth's atmosphere is held in place by gravity, which pulls the gases toward Earth. The pressure caused by the weight of the atmosphere is called atmospheric pressure. Atmospheric pressure is exerted on everything on Earth, including you. At sea level, the atmosphere exerts a pressure of about 101,300 newtons on every square meter, or 101,300 pascals. So, there is a weight of about 10 newtons, or about 2 pounds, on every square centimeter of your body. Why don't you feel this crushing pressure? Like the air inside a balloon, the fluids inside your body exert pressure. This pressure inside your body acts against the atmospheric pressure. Figure 2 can help you understand why you don't feel the pressure. Variation of atmospheric pressure. The atmosphere stretches about 150 kilometers above Earth's surface. However, about 80% of the atmosphere's gases are found within 10 kilometers of Earth's surface. At the top of the atmosphere, pressure is almost non-existent. The pressure is close to 0 Pascal because there are fewer gas particles and they rarely collide. The small number of gas particles is one of the reasons it is harder to breathe at high altitudes. There isn't as much air. Mount Everest in South Central Asia is the highest point on Earth. At the top of Mount Everest, atmospheric pressure is about 33,000 pascals, or 33 kilopascals. People who climb Mount Everest bring oxygen tanks to help them breathe at that altitude. At sea level, atmospheric pressure is about 101 kilopascals. Atmospheric pressure and depth. Take a look at Figure 3. Notice how atmospheric pressure changes as you travel through the atmosphere. As you travel farther down into Earth's atmosphere, pressure increases. In other words, the pressure increases as the atmosphere gets deeper. An important point to remember about fluids is that pressure varies depending on depth. At lower levels of the atmosphere, more fluid from above is being pulled by Earth's gravitational force. So, there is more pressure at lower levels of the atmosphere. Pressure changes and your body. So, what happens to your body when atmospheric pressure changes? If you travel to higher or lower points in the atmosphere, The fluids in your body have to adjust to maintain equal pressure. You have experienced this adjustment if your ears have popped when you were in a plane taking off or were in a car traveling down a steep mountain road. The pop happens because of pressure changes in air chambers behind your eardrums. Water pressure. Water is a fluid. So, like the atmosphere, water exerts pressure. Also, water pressure increases as depth increases, as shown in Figure 4. As a diver goes deeper into the water, pressure increases. The pressure increases because more water above the diver is being pulled by Earth's gravitational force. Also, the atmosphere presses down on the water. So, the total pressure on the diver includes water pressure and atmospheric pressure. Water pressure and depth. Like atmospheric pressure, water pressure depends on depth. Water pressure does not depend on the total amount of fluid present. A person swimming 3 meters below the surface of a small pond feels the same pressure as a person swimming 3 meters below the surface of a large lake. There is more water in the lake than there is in the pond, but the pressure on the swimmer in the pond is the same as the pressure on the swimmer in the lake. Density and water pressure. Water is about 1,000 times as dense as air. Density is the amount of matter in a given volume, or mass per unit volume. Because water is denser than air, a certain volume of water has more mass and weighs more than the same volume of air. So, water exerts more pressure than air does. For example, if you walk up 3 flights of stairs, the decrease in atmospheric pressure is too small to notice. But if you dive underwater the same distance, the pressure on you increases to 201 kilopascals, which is almost twice the atmospheric pressure at the surface of the water. Pressure differences and fluid flow. When you drink through a straw, you remove some of the air in the straw. Because there is less air inside the straw, the pressure in the straw is reduced. But the atmospheric pressure on the surface of the liquid remains the same. Thus, there is a difference between the pressure inside the straw and the pressure outside the straw. The outside pressure forces the liquid up the straw and into your mouth. So, just by drinking through a straw, you can observe an important property of fluids. Fluids flow from areas of high pressure to areas of low pressure. Pressure differences and breathing. Take a deep breath. Fluid is flowing from high to low pressure. When you inhale, a muscle moves down in your chest. This movement makes the space in your chest bigger, so your lungs have room to expand. This expansion lowers the pressure in your lungs. The pressure in your lungs becomes lower than the air pressure outside your lungs. Then air flows into your lungs from high to low pressure. Figure 5 shows the reverse process when you exhale. Exhaling also causes fluids to flow from high to low pressure. When you exhale, the air in your lungs flows out from a region of high pressure, inside your chest, to a region of lower pressure, outside your body. Pressure differences and tornadoes. Look at the tornado in Figure 6. Some of the damaging winds caused by tornadoes are the result of pressure differences. The air pressure inside a tornado is very low. Because the air pressure outside the tornado is higher than the pressure inside, air rushes into the tornado. The rushing air causes objects to be pushed into the tornado as though the tornado were a giant vacuum cleaner. The winds are usually very strong and affect the area around the tornado. So sometimes, the winds damage trees and buildings that are not even in the direct path of the tornado.